첫 번째 발표는 한국화학기술연구원에서 하칸카라수 연구원께서 발표를 진행해 주시도록 하겠습니다. So let's start.
Good afternoon, everybody. Welcome to my presentation. So today I'd like to talk about electrochemical deactivation for electrochemical CO2 reduction, implementing explainable artificial intelligence. So the content of the research, in the first chapter we have the research background, overall flow work, experiment, and GMAP. And it's continual model architecture and explainable AI model. And the last chapter it will be the surface analysis of the catalyst. So basically, the electrochemical system is play an important role from all the process. That's why I place it into those. I centralize it in this PPT. So especially the electrochemical reduction of the CO2 to CO can be. The electrochemical cell can be derived by the electricity from the renewable energy, and as far as I know, from the electrochemical CO2 reduction, 16 components can be obtained out of the CO2 reduction. So we can use it as a chemical feedstock, and we have the energy storage, and we can use this chemical feedstock as energy storage. So on the top, we have the utilization. I think the picture it is taken from the cement production. So during the cement production, huge amount of the CO2 released into the atmosphere. So by using the CO2 capture utilization, I mean, in there we have the electrochemical system. So the main problem of what is the main problem of this electrochemical system? The electrochemical system, for example, besides the activity and selectivity, one of the problem is the catalyst degradation and bicarbonate salts generation, and other problem, which is one of the biggest problem as a scientist, we have got to figure it out, the competing hydrogen evaluation reaction. So what is our purpose? What we have done in this project? The purpose of this project was to measure the performance of the catalyst using the explainable artificial intelligence. So what we can do, what we have done in here, we are able to predict the Faraday efficiency of the carbon monoxide or the cell, the Faraday efficiency of the hydrogen and total current. And apart from that, we can understand the degradation pattern, I mean the long-term degradation pattern of the catalyst. This is really important for especially in terms of the commercialization. So, we can create, using huge, large data set, a development platform for the catalyst stability. So, as I said, we have the real world problem, and we capture the data, we have the deep neural network, and we use the model, the black box model, which is DNN, and then we have the interpretability, which is the GradCam method we propose, and lastly, it is the interpretation. So, as you can see, we collect our data set from the electrochemical experiment, and once we collected the data, we propose a neural network. Then we have the surface analysis measurement. On the right side, we have the GradCam result, and we validate the GradCam result by using the surface analysis measurement, such as how the extrinsic and intrinsic properties of the catalyst is changing throughout the long-term stability. So this is the method on the right side. We propose and discover during the experiment. We have the nitrogen as speaker. Since the nitrogen is inert gas, it doesn't react with any other component, I mean the chemicals. The second, we have the CO2 LSB curve. So actually the neural networks, it can capture the nitrogen, the LSB curve of the nitrogen, and CO LSB curve. What I mean by the LSB is the linear step alternative for the catalytic activity. It is measurement. So each performance, like our neural network, it can understand the nitrogen LSB curve and basically the nitrogen LSB curve can reflect the CO2 LSB curve. That's why our neural networks and our prediction is quite high. So we have in total 6 long-term stability of the different catalysts and different condition and different membrane. So we can clearly say that this the silver, based on the silver base, we have the promising long-term stability, especially at 3.2. On the right side, we have the UMAP, uniform manifold projection. This is the feature reduction. We would like to connect from the higher dimension to the lower dimension, and we would like to visualize our old data set into the 2-dimensional. And this shows that the LSB and Faraday efficiency correlated independent of the cluster type. So this is our proposed 1-dimensional convolutional neural network. We have the CDM in order to increase the performance. What I mean by the CBM, it is the spatial attention and channel attention. It's composed of the spatial and channel attention method. And by implementing this, we can see what or where information is become important in LSB curve, and we can improve the prediction. And this is our prediction result. As you can see, like we have the promising prediction for electrochemical cell, especially for electrochemical cell for Faraday efficiency of the hydrogen and CO and total current. So after we have the prediction why our prediction is high. We would like to know which part of our input data set it has the what makes the input make this prediction, and we would like to know that reason. That's why we propose, after the prediction, we propose the GradCam model. So on the right side, based on the importance method, we have the GradCam result. In the next slide, I will talk about that. So this is our GradCam result. We can see, I just put it in here, two different catalysts. We have at the top we have the silver-based catalyst. At the bottom we have the nickel-based catalyst. So we can see that actually our attention method is focused on the after the onset potential. Where is the onset potential? As you can see, the white dashed line, it represents the onset potential. Our attention region, it is the GradCam model is focused on our attention region after the onset potential. So as you can see, on the x-axis is representing the Faraday efficiency of the CO, and the y-axis is the LSB curve, and the GradCam we can clearly say how the performance it is dropping throughout the long-term stability. For example, the reason why in the case of the silver we have the bicarbonate generation. So when the bicarbonate generation stick to the silver nanoparticles, and the performance drop. So each cyclic, this requires, for example, in order to run the reaction, it requires higher overpotential. So we can clearly say also we have the toughest slope in terms of the performance. At the high Faraday efficiency, we have the wider attention region. As the performance drops, the Tafel slope increase. As a result of that, our performance, the Tafel slope increase, which means that we have the lower kinetic region. Also, we have another issue when I talk to biocarbonate generation, because the biocarbonate generation is below the surface of the GDA, the gas diffusion layer, especially the block there, and the CO2 cannot penetrate and blocked in that surface. So in the case of the nickel, we have in the x-axis it's representing fire efficiencies of the CO. But as you can see in here, the active side in the case of the nickel, because in terms of the long-term stability, the nickel's performance dropped sharply compared to the silver. We would like to know that the reason. The reason is actually coming from the intrinsic properties of the catalyst, which is at the beginning the active side it is decreasing, and then we have the attention region, and then the active side is keep decreasing. On the last part, when the performance is dropped, the metal center of the nickel is completely detached and very low kinetic region and diffusion region, and there is no diffusion region on the last part is dominant anymore. So in here, like we can see from the DLC figure, the gradient of the LSV curve with respect to the overpotential, we can see that at the beginning, from there, we can see that how the diffusion current, I will show in here. For example, in here, the diffusion current is dominant, and when we look at this inflection point, it is, as you can see, the diffusion region is not dominant anymore in that region. So that's why the active side is consuming throughout the experiment. So, as I said, this is the intensity, the binding energy, the X-case result. As I said, in case of the silver, we have the potassium bicarbonate. The potassium bicarbonate, it is stick on the surface of the silver nanoparticles, and the performance is dropped. However, in the case of the nickel single atom catalyst, actually the active side, it is nickel, the composed of the nickel N. So the performance, the long-term, the stability is continuous, and the active side, there is no nickel N in this section and in this section as well. So as you can see here, after the performance is continued, the acceleration is happening. So as a conclusion, what I can say in here is that based on our explainable neural network, we can measure, or we can understand the extrinsic and intrinsic properties of the catalyst through the explainable AI. So this is the conclusion of our project. So thank you. 감사합니다.
Thank you so much. Is there any questions? 질문 있으신가요? Okay, one question. So, it is possible to apply this methodology to different catalysts? Not only for the electrochemical CO2, but also like thermal catalyst or something like this?
That's what I believe. I think based on the methods which we propose during our experiment, definitely it's possible, because as you can see, the neural network, it can understand the sequential data, and it is definitely possible. I will say that.
Okay, thank you. 다시 한번 발표해 주신 연구원님께 박수 부탁드립니다.